All right, so let's get started. Still in chapter 16 here. Um, Again, the first reminder will be the homework is due Thursday. Okay, so if you haven't started working on them, make sure you start work on them soon. Okay. Um, today's for in-seat classroom disinfection, Joshua and Isaiah. Okay. All right. So so again, briefly, last time we checked at the relationship between the speed of wave in a stream with the tension and then the mass density. We did this by looking at dimension consistency from both sides of the equation, and we figured that the speed of wave on the stream should be equal to square root of the tension force in the stream divided by the mass per length of the string. Okay, so it's the linear density of the string. All right. This time we are going to check the energy and power of a wave. So I think each year there's several like earthquake happening around the globe, and some of them could be very destructive. So something like this showing in the figure. So when earthquake hits, it comes coming in the form of wave. Okay, so let's take a look on the energy in a wave. So take a look on a simple case of stream. You have a wave in the stream. So then if you look at the small portion of it, delta M here, so we know that the mechanical energy over here or kinetic energy over here, if this is moving up and down, it should be equal to 1/2 the mass times the V squared, right? Because this for the string is going in the y direction. So you just focus on the y direction here. And this is the mass for that small portion of it. So U will be the mass per length, per unit length. So then the per unit length density times the length delta x, okay, will be the length of this small portion. That will be the mass. So 1/2 mv squared will be the kinetic energy, okay? So in the case, if you approximate delta x to 0, then you are looking at the decay, the infinity decimal fraction of the kinetic energy, right? So if you are doing that, that means you are doing differentiation of it. So then dk is equal to 1/2 mu. Now you change delta x to be dx, all right, and then v squared. For the position of the median, it's going to be either a sine function or cosine function. So take example of a sine function here. It's also a function of time t and x. So it's x and t, function of x and t. So then take this y here. So then you will have vy, the speed of that portion of the string there. It's going to be, again, partial derivative of the displacement position function divided by dt. Okay, it's going to be minus a omega cosine, which we check I think 2 lectures back. Then dk is going to be equal to 1/2 again. So 1/2 this guy. Now vy should be replaced by this expression. So then that's squared. Okay. So dk then equals to 1/2 mu dx. A will be the amplitude squared. Omega will be the angular frequency of the wave squared. Cosine square of kx minus omega t. Okay. So this is the energy in that small part of the stream. All right, and then you can imagine as the earthquake hit, the wave of earthquake hits, then it carries similarly the amount of the energy just in this form, kind of in this form. It might not be exactly a cosine function or a sine function, but could be related to the amplitude and the frequency. Okay. All right. So clearly there's energy in the wave, right? Carried by the median. Now, when we talk about energy, sometimes we are more focused on the energy, the intensity of it. Okay, so remember, intensity should be equal to the energy, or this is the definition for the intensity. It should be the energy going through a certain point. All right, divided by the area of that energy going through, and then divide by the time t, the impact time t. Okay, so that's the density of it. Now remember, when we give out definition for power, power is defined as the energy over which time of impact. Okay, so E over T is equal to power. So then intensity can be rewritten as just power divided by the area. Okay, so in this case, you can see that intensity then should be having a unit of watts, which come from power divided by area. Okay, so area will be meters square. We use I for intensity here. Okay, a lot of cases, for example, when the radio wave is propagated from radio station. Okay, so then the wave propagates in like this three-dimensional spherical fashion. So it comes start from one point and then radiate out. Okay, so in that case, at a particular point, that is distance r away from the point source, then at that location, intensity should be equal to the power of the radio station, for example, divided by the area, which should be a spherical. Okay, in three-dimensional, it's a spherical area. So power radio station should be given, or should be fixed, right? Because it has a certain power there. All right. And then when a wave is generated, for example, sound wave is generated, it's kind of like from a point source and then propagate out radically in that fashion as well. So it's also can be intensity can be calculated by doing power divided by 4 pi r square. Okay. Now in biological world, some animal gives out like waves, sound waves. For example, a bats. Okay, a bat, they will give out the sound wave, and then according to the wave left reflect back from the target, the mouse here, they can kind of, I guess they have a supercomputer in their brain, so they can calculate how far that is a mouse is away from them. But yeah, I don't think I can do that, but they can do that. Okay, so the wave that the sound wave that the bat gives out. Okay, so it's also a point source coming from a point source, and then you can calculate what's the intensity by the equation two. Okay, all right. So that's the energy in the wave, and then sometimes if you are concerned about what's the intensity, you can use the formulas given there to calculate the intensities. Okay. Um, So I don't have an example right now for that section, but later on I think we probably have one or two example on intensity. But we are going to move on to the next section here, interference of waves. Okay, so one wave meets another wave, they will kind of interact. Okay, so how do they interact? That's the focus here. Before we look at any two or three waves coming together, let's take a look on the interaction of wave with a median here. So for example, if you have a string over here, one end is attached to the wall here, and then if you send in a wave, okay, so just say if you shake this string up and down, it will generate a wave like this, okay, and then it will be propagating through here, and it will hit the wall here. And when it comes back, all right, actually the wave peak will reverse and then going backward. Okay, so this is what will happen. All right, this is when one end of the string is being fixed. Okay. On another hand, if you have a string that is kind of having a free boundary here, condition here, so it's going to tie to, it's not actually fixed over there, but with a rod going through here, there's a circle, open circle over here, okay? If you're sending a wave here, if this side is free to move, then actually the wave peak will come back, okay? As a peak, not a valley, all right? So this is what happened. So we call this flip as a phase change, all right? If it comes back, if the peak come in, reflect back as a valley, then it has a phase shift of 180 degrees, okay, or pi, all right, in radians. Otherwise, there's no phase shift, all right. Another scenario is when you have the median that is made of, say, two parts. So the string here, one end is thinner than the other end over here. Okay, so if that happens, if that's the case, now as you send in the wave from one end over here, then the wave is going to split into two parts. So with one part going into the second part of the string over here, with the same like from as it comes in as peak, it goes out as peak. Okay, now the second end will be reflected back because there's density change in the string over here. So this is look like acts like a wall over here. All right, when it hits here, then bounce back. Okay, the second part of the wave comes in back over here, but there's a phase shift. If you have a peak comes in, then reflect back as a valley comes out, okay, over here. So two parts, transmission part and then reflection part, okay. If you send in the wave in the other way around, so you send in the wave from the thicker part over here. So again, one part will be transmission, called transmitted wave. The other part will be reflected wave. So transmitted wave is again here, if you send in the peak in, it will be a peak. But for the reflected wave, if it's a peak in, reflected back as a peak. Okay. So then there's no phase change here. From thinner median to a thicker median. So in this case, you have for the reflected wave, you have phase change of 180 degrees or pi. From thicker median to thinner median, in the reflected wave, you do not have that phase change. Okay. Now this is significant when we talk about light refraction later in the semester. Okay, but keep in mind, you are going from thicker to thinner. The reflected wave does not have phase shift. Otherwise, it does. Okay. All right, now let's take a look. If you have two waves, they meet at certain point. So in the stream here, you have one wave comes from left to right, the other one goes from right to left. Okay, they will meet at certain point in the middle over here. All right, so when they meet, they will add up. Okay, so this is called the superposition of the two waves. All right, and then after the brief meeting over here, so the wave goes from left to right, continue to go from left to right, propagating to right, okay? The other one continue to propagate to the left, okay? So they behave like they never met before, just continuing like that. But in a place they meet, they will add up, okay? So this is the two same waves comes in like peaks, meet peaks, okay? On the other scenario, this is what happens when you have one wave that is identical to the other one. When they meet at the same location, they add up. Okay, so you can see the amplitude adds up here, right? Now, on the other hand, if you have a peak comes in where it meets a value from the other one, then those will cancel out if they have exactly the same amplitude. Okay, otherwise they will just be partially canceled. All right. So this is called destructive interference of the two waves. And then the previous one is called constructive interference. Okay. So from the wave function here, you can see when destructive interference happens that when that happens, the initial two waves, they have a phase difference of 180 degree. Okay, so these two waves, I mean, they look pretty much the same with the other one, but with a phase shift, right? If you shift this guy 180 either to the right or to the left, then it's identical as this one. Okay, so if there's the difference in phase of 180 degree or pi, then they will cancel out. That's called destructive interference. On the other hand, in the previous slide here, you can see they're identical. There's no phase difference between these two, so then they will add up. Okay, it's called constructive interference. All right. Now, in general, you probably don't have the situation that the phase difference is either 0, means no phase difference, or 180 degree, right? In general, you may have a phase difference of any number, say maybe 45 degree, maybe 30 degree, etc., but not 0 or not pi, okay? So if that's the case, then we'll say if one wave function comes as this guy, the other one has a different phase than that one, by any number of delta, we can call it delta, okay? Could be 5 degree, could be 55 degree, whatever, okay? So then when the two meets at certain point in space, these two will add up, okay? So basically you just add these two trigonometry functions up, okay? That's the result then. So then y1 plus y2 will be equal to a sine of kx minus omega t plus a sine of kx minus omega t plus delta. All right. Now they have the same amplitude, so then you can single out amplitude. So then you'll just add these two trigonometry identities up. Okay. So if you need a review, you probably have to look up the table for the trigonometry and identities. So like a sine plus a sine. So a sine, say sine theta 1 plus sine theta 2, the result will be 2 times of cosine, 1/2 of the difference of the two angles, times sine of 1/2 of the addition of the two angles. Okay, so this is the two sine function add up. All right. So then you apply that relationship here, you'll get this result. Okay. So it would be twice times the amplitude cosine, the 1/2 the difference of the two angles or two faces will be delta, and then sine of the addition of the two. Okay. So then it would be 1/2 of addition of the two, because 2kx will become kx, and then 2 omega t times 1/2 will become omega t, but delta will be divided by 2. Okay. So as a result, you can see this is a generalized expression for y1 plus y2. Okay, if in case delta equal to 0, that means the two waves in the plot is the red and the black ones. They are identical, so then they add up. Okay, and then if delta is equal to 180 degree or pi, then they will cancel out. Okay, when they add up, when delta is equal to 0, this is called the two wave function are called in phase. That means their phases are the same. Okay, the argument in the sine function or cosine function are the same. Okay. All right, so the result will be constructed interference. When delta is equal to 90, that means they are having a phase shift of 180 degree or pi. Then they are called out of phase. They will be canceling out each other. That's called destructive interference. Okay. So this is what happens in the mathematical point of view for the two waves to interact with each other. Okay. Let's take a look on this practice problem. It says you have two waves with the same frequency, wavelength, and amplitude. Okay, are traveling in the same direction. All right. If they differ in phase by 90 degrees, so that means delta is equal to 90 degrees. Okay, the small delta, and each has an amplitude of 4.00 centimeter. What's the amplitude of the resultant wave? For the phase difference delta will be, or for what phase difference delta will be, will the resultant amplitude be equal to 4.0? Okay. Now it says they have same frequency, same wavelength, and amplitude. So that means you can write them either as a sine or cosine. We'll take the sine as what we did in the slides. So you can say y1 is equal to a sine of kx minus omega t. You can say y2 is equal to a sine of kx minus omega t, but with the phase difference of delta, small delta here, okay? So in first part is asking you if delta is equal to 90 degrees, okay? And then each of the a is 4.00 centimeter. What's the new amplitude? A prime, let me say A prime. Now, if you go a couple slides back, you realize that in this case, y1 plus y2, that's the new wave, right? When the two meet becomes a new wave, it has this 2a cosine delta divided by 2. That's the amplitude, the new amplitude A prime, okay? And then sine of kx minus omega t plus delta over 2, okay? So if you go back to the problem here, it's asking you this A prime, okay? Now simply delta is equal to 90, okay, you can calculate that. And B is asking for what phase difference delta will be. So now it's asking you if A prime is equal to 4.00 centimeter, then what would be that? So this is probably a different delta, right? It's a different delta. You can call it delta prime. Put this way over here. All right. So let's take a look here. So this is the new amplitude. Okay. So as I mentioned here, so you're looking for this one. So here you simply just plug in numbers. This is equal to 2 times 4.00. That's in centimeter. And then you're going to do cosine of 90 degree divided by 2, right? So then that will give you 5.66 centimeter, okay, on the part A there. Part B here, you're looking for delta this time. So it tells you the new A prime is 4. So that means, so A prime equals 2 times A cosine of delta 2. Let me call this delta prime. You're looking for delta prime, okay? So 4.00 equals to 2 times 4.00 centimeter. That's the same cosine of delta prime divided by 2. You're looking for this guy, right? So 4 and 4 can cancel out, right? So then you can move the 2 to the other side of the equation. That means 1/2 equals to cosine of delta prime divided by 2. Okay. They can do, so if you are very familiar with trigonometry, you probably figure out, okay, so cosine of 60 degrees should be 1/2, right? So then this is 60. So then delta prime should be twice of that, 120, right? Divide by 2, so it gives you 60. So then that's 112, 120, okay, degrees there. All right. Otherwise, you can do cosine inverse 1/2. That should give you 60 degrees. Then you can do the same there. Okay. All right. Any questions from you guys? Okay. So if not, then we can move on here. So we have talked about the same identical waves. Okay. A lot of times when you have two waves meet at one location, they are not necessarily having the same source. Okay. So you could well have like sources, waves coming from different sources. Okay. So like source 1 and source 2 in this figure here. All right. Now, the fact that they meet over here, so the x here will be the distance from the source to the point of interest. Okay, so then this is x1, this will be x2. All right. Now you can have them. So typically, this is in the lab. This is what you would have. You will have like two speakers. You can plug them into the same source, so they can have the same frequency. Okay, to start with. So then frequency can be the same. Frequency is related to angular frequency. Okay, so angular frequency is 2 pi times frequency. Okay, so that's the same there. But now for the wave numbers, you can have the same because you are connecting them to the same source, right? But then x1, x2 could be different, right? So then from here to there, from here to there, there will be a difference, okay? If you are doing, if you send them both sources with a sine function, exactly the same sine function, so then the difference in their phases, okay, is starting with a sine function, then you'll be taking difference of this guy and that guy, okay? So, or basically you are starting from, say you are starting from, for the source, the waves comes out the two sources, and you can write one as y1, right? y1 equals to an amplitude sine of kx1 minus omega t. And then y2 equals to a sine of kx2 minus omega t, right? Because they are not having the same path, so then this x1 and x2 are different. Okay, it's from the source to the point of interest. Okay, so you can write out as this one. These two expressions. Okay. All right. So then in reality, This is because in this scenario, so the difference in their phases would be equal to due to the difference in their paths. Okay, so k times delta t. Omega t can cancel out. Okay, now delta x would be x2 minus x1, the difference in path. Okay, of the two waves. Now you can see mathematically again, like what we learned before, if delta is the same, right, then they are in phase. The two waves, they are in phase. Then they will, when they meet, they will add up, meaning they will have constructed interference. Okay, so then this phase, okay, k delta x could be equal to well, let me see. So if they are in phase, I think there's a step missing here. So delta is equal to k times delta x. All right. If delta is equal to 0, that means those two are in phase, right? Then they will add up. Now, other scenarios you can consider, if they are equal to 2 pi, that means 360 degrees. Okay, so I think in this case it's easier to use 2 pi's or 4 pi's, 6 pi's, etc. Okay, then they should also be called in phase, because for a sine function, if you add 2 pi to it, then it repeats itself, right? For one period, and then add a 4 pi, it will repeat itself as well. So in phase really means they are this guy is equal to 0, 2 pi, 4 pi, 6 pi, etc. All right. So then this is constructive interference. Constructive. Okay. On the other hand, if delta equals to I think a pi, 3 pi, 5 pi, 7 pi, etc. Okay. So again, because if you add 2 pi, 2 pi, then it becomes 3 pi. Okay. Then it repeats itself because it's one period. Okay. Add to the function. So for destructive interference, that really means their phases are off by the odd numbers of pi's, right? Like 1, 3, 5, 7, etc. of pi's. Okay. And then if they are constructed interference, that means 0, 2 pi, 4 pi, etc. Okay. All right. Now so that means, okay, kx, if they are equal to 0, 2 pi, 4 pi, etc., then it's constructed interference. Now remember, k is equal to 2 pi over lambda, right? K is the wave number, is equal to 2 pi over lambda. All right. Times delta x. Okay. So then equals to 0, 2 pi, 4 pi, etc. Okay. So 2 pi will cancel out here. It becomes 1, 2, and then 3, etc. Right. So that means delta x times lambda is equal to 0, 1, 2, 3, right? So then delta x is equal to either 0, you multiply both sides by lambda, or pi, or 2 pi, or 3 pi, etc. Okay. Then that is this condition listed over here. So that's when the constructed interference happens, when the path difference of the two waves, yeah, 0, pi, 2 pi, 3 pi, etc. Okay. Now, similarly for destructive interference, you can set this kx equal to pi, 3 pi, 5 pi, 7 pi, integer numbers of pi. Then you will figure out that for destructive interference to be happening, you have to have delta x equal to either 1/2 pi. Sorry, it's covering that, but the last line on the slide here, it says delta x should be equal to 1/2 of pi, 3/2 of pi, 5/2 of pi, 7/2 of pi of lambdas, okay, etc. So it's basically halves of lambdas, okay, integer number or the odd number, odd integer numbers times half of pi, okay. So then you have destructive interference. All right. So then for two waves, if they have difference in path due to path, the difference in path delta x, f is 0 pi, 0 lambda, 2 lambda, etc. You have constructed interference. If you have 1/2 lambda, 3/2 lambdas, 3/2 lambda, 5/2 lambda, then you have destructive interference. Okay. Now that's for this these two conditions to be valid. That's because that's when the two sources are in phase. Okay, so that means um, initially when they start with the sources, they are the same phase. Okay, there's no phase difference. However, if the two waves coming out from two sources, they originally have opposite phases. That means they were originally off by a pi or 180 degrees. Then the conditions are flipped. Okay, so if the change in path or the difference in path lengths are 0, lambda, 2 lambdas, 3 lambdas, then you have destructive interference. Okay. On the other hand, if the delta x is half lambda, 3/2 lambda, 3/2 lambda, then you have constructive interference. Okay. So you also have to be careful about the sources if they are in phase or they are opposite in phase. Okay. Initially. All right. Let's take a look on one example here. I think this one is very similar to one of the homework problems. Okay, so this one says you have two speakers. Now pay attention here. It says originally the two speakers are out of phase. Okay, so out of phase speakers, they are separated by 3.5 meters. A person standing against the wall is 5.0 meters away from the two speakers in this direction. Okay. Now, if the person is standing at the midway between the two speakers, hears destructive interference. Okay, so this guy hears destructive interference when he is at midway. Now he moves 0.84 to one side along the wall and hears the constructive interference this time. So that means over here he hears like the probably like lower sound. And then when he's here, or weaker sound here, when he moves here, then he hears the stronger sound. Okay, so that means the constructive interference. Destructive interference over here, constructive interference over here. Okay, so it's asking you what's the frequency of the sound emitted by the speakers, assuming the two have the same frequency. I think let me sketch the problem here so you can get started with the figure here. So initially, this is the wall. I'm going to just use 2 points for the two speakers. Okay, you can treat them as point sources. So S1 here, S2 here. These two are 3.5 meters apart. This is 5 here. Okay, when he's midway here, approximately. I can stop sharing now. So you can see better. So originally he's here. So then this is X1. This will be X2. Okay, X1, X2. Now, if he moves about 0.84 meters to one side over here, wave comes out of S1 will be propagating along this path, okay? And then wave comes out from X2 will be propagating along this path over here. Now this is X1, this is X2, right? This is 0.84 meters. This guy is 5 meters. This is midway. So this is 0.84 meters then. Okay, that's same as amount up there. So when he hears the distract interference at this point, because these two are out of phase, okay, so the two sources are out of phase, So that means they are differ by 180 degrees or pi. So in that scenario, they have the same path, right? So there's no path difference. So that means delta x is equal to 0 initially. So then you hear distracted interference, right? That's exactly what the condition should be. Now you move it by that much. So then now your x1 and x2 changes, right? They both change, right? So then no longer if you do x1 minus x2, the new delta x is not going to be 0, right? But it's going to be related to the wavelength because this time you hear constructed interference, okay? So then if you look at the condition earlier, you flip a couple slides back. Let me see if I can bring that up here. Just quickly. If you guys are online, you can flip one slice back. Okay, so this is when the two are in opposite phases for constructed interference, then the path difference should be half lambdas. Okay, so when he moves by that amount, he probably hears this first constructed interference. Okay, so that means the difference in their passes x1 minus x2 is equal to 1/2 lambda. Okay, so this is equal to 1/2 lambda to hear the constructed interference. Okay, so what will be the frequency? It tells us the speed of the sound wave as 340 meters per second. And then it asks us to find what's the frequency. Okay. There's a relationship between speed and frequency. If you remember, speed of a sound should be equal to lambda times the frequency, right? So if you can figure out what's the lambda, then you probably can figure out the frequency. Okay. And you probably can figure out lambda from here. All right. So let's take a look here. I think I see a few guys says 202, and then I think I know where this little one come from. Okay. So you probably said x1 minus x2 is equal to 0.84 meters. And then that's equal to lambda over 2. Then you figure out lambda is twice of that, right? And then once you have lambda, you take that into this to figure out the frequency. I think that's what you did. But actually, the difference is not just 0.84, okay? Because you move 0.84, now x1 becomes this hypotenuse of this triangle. X2 is the hypotenuse of this guy. So you really be looking at what's new x1 and x2 and then do the difference of the two, okay? x1 minus x2, it's not this guy, okay? So you have to solve x1, x2 from geometry over here. So this is a right angle here. So for this guy, it should be square root of this square plus this square, right? So x1 will be equal to square root of, if this is a, this is b, this is c, right? So then c is equal to a squared plus b squared. So this is really, so the whole thing is 3.5, halfway here to here should be 1/2 of that. So 1/2 of 3.5. You moved by that amount, so plus that amount, okay? Squared. That will be your x1, all right? And then your x2 will be this, again, 1/2 of 3.5 minus this guy in this time, okay? This time you subtract 0.85 off that. So 3.5 divided by 2 minus 0.84. And then squared. All right, I think on this one here, this is just one side square, right? And then plus this vertical square is 5.0 square. And here plus 5.0 square, okay? And then you'll take the difference of those two, right? So x1 minus x2, so then equals to lambda over 2. I think I did them just everything together. I basically do, so this is lambda, so this is half lambda. So then lambda is equal to twice of x1 minus x2. So what I did is lambda equals to twice of the 2 square root, okay? The first one minus the second one. I did that way. So then my lambda is 1.098 meters, okay? It's not 1.68, but it's 1.098, all right? So that's how you need to figure out your lambda here. Once you have your lambda, so then the frequency will be equal to the speed divided by lambda, okay? Speed is 340 meters per second divided by 1.098 meters. That gives you 310 roughly hertz as your frequency, okay? All right. Let's see if I can capture everything here. All right, so that was not right. Questions you guys might have? Okay. So quickly, the next section here talks about beats, okay? So I think we have talked about the difference in paths. If the two waves arrive at the same location with different paths, then there's a result of that. So it leads to change in phase. Now, similarly, if two waves coming out of their sources, if their sources are differ slightly by frequency, then when they arrive at the same location, the argument in the sine function, they should also differ slightly. Okay, so that cause the difference in so the difference in frequency will lead to difference in phase again in that case. Okay, so this time I'm going to show you a wave function by cosine function, but it could be a sine or cosine function. Okay, either way. But in this case, cosine function, if their frequency are slightly different from each other, then when you add the two up, so this should be y1 and y2, okay? Not gamma 1, gamma 2. But if you add the two up, y1 and y2 up, they will be equal to this guy, okay? So again, you start with cosine function, you end up with cosine function. With this guy will be small. So then this whole thing will be your new amplitude, okay? 2a times cosine of this will be your new amplitude, all right? So these are the two waves originally. When they meet at one location, this is the resultant, okay? Or if you zoom in to see, you'll see that the amplitude of resultant changes, but actually oscillates, okay? So comes down and goes up again, comes down, goes up again, okay? That's because the new amplitude is a cosine function, as you saw in the previous slide here. So the new amplitude here is a cosine function, so it actually kind of also oscillates, like decrease and increase, increase and decrease, okay? The frequency variation here is called the beat frequency, okay? Beat frequency is absolute value of the differences of the two frequencies, okay? So that should be an absolute value, all right? Okay, I think that's how much I want to include in today's class. Okay, so I will stop here, and then just a heads up. So tomorrow for the lecture, we all meet online. Okay, so just Tuesday we meet all online. All right, and then if you are sign up for the lab tomorrow, we'll be meeting here in the afternoon. Okay.